Hello, everyone. Good evening, good morning, good afternoon, wherever you are. My name is Gio. I'm a student here at Lutheran High School, and today we'll be doing a calculus lecture on section 3.7, which is optimization. Now, one of the most common applications of calculus involves the determination of minimum and maximum values. And that is essentially what optimization problems aim to do, is to find minimum and maximum values in order to find what is optimal or ideal. And you can think about some terms that you hear or read that relate to this very thing that we're talking about, such as greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, greatest distance, etc. And you see those a lot in everyday life, and it's important to find out what those things are in life and in calculus. So that's why we are learning this. And just a basic, to get a basic understanding of optimization, imagine a person wants to design a box with a surface area of 100 centimeters cubed. What dimensions would produce a box with the maximum volume? So there are a couple of things we know, and there are a couple of things we don't know. We do know that the box we're talking about is a rectangular prism, and that its surface area is 100 centimeters cubed. Now, what we don't know, and what we need to find out, are the dimensions and the volume, of course, because the volume determines the dimensions. So with optimization problems, we actually try to find these things out. And there's a few steps we can take to ensure that we do this right. Now, before we can begin to understand optimization problems, we must know the definition of optimization. So, that's the first thing we're going to write down here is our optimization definition. So, as we discussed, the definition of optimization by the book is to find the optimized or ideal value of something. So, pretty simple. And some terms you want to look for in the word problems, terms to know, include things such as greatest profit, least cost, least time, and greatest voltage. Of course, this list is not all inclusive, but if you pick up on keywords and things like those, you will be going in the right direction. So, greatest profit, least cost, least time, greatest voltage. Those are just a few examples. So, now to the sample problem. We are going to go with a classic example. So, a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He doesn't need fencing along the river. What are the dimensions of the field with the largest area? So there's our keyword right there, largest area. So that's what we need to find out. So on to the solution. So our first step, we got to start with step 1. And step 1 happens to be pretty simple. Excuse me. All you need to do for step 1 is draw a picture. Now, it's important to draw a picture so that visually, for the rest of the problem, you know what you are doing. So, for this problem, we would draw our river. So here's our river. And our fencing. And we need to make sure that we represent our drawing with symbols. We need to make it mathematics, so you'd have this represent our width, x, and y represent our length on the sides. And there's our rectangle with x and y representing the sides. Step 2. Step 2 is to identify the primary equation. So, the primary equation is, in essence, the thing that is to be optimized. So, in this problem, the thing to be optimized is area, the largest area. It's pointed out right here. So, the formula for the area of a rectangle we know is area equals length times width. And since we represented our drawing, we don't have any L and W variables, so area actually equals x times y. So we did that. That is our primary equation. Step 3. Is to find a secondary equation. We have a primary equation, a secondary equation. This is also called the constraint because it limits, it's the limit of our problem. So, and if you look in the problem right here, 2,400 feet of fencing, that is our limit, and that limit is perimeter. That's all that we can use. So the length of the fence is perimeter. And perimeter of a rectangle equals 2 times length plus 2 times width. Therefore, we already know that the perimeter is 2,400 feet, as indicated right there. So 2,400 equals x plus 2y. And the reason we don't have 2x plus 2y is because he doesn't need fencing along the river. So that's why we don't have an x right here. We only have one x and two y's. So that is our constraint. On to step 4. Is to solve the constraint for a single variable and plug this into the primary equation. So we need to solve the constraint for a single variable and plug this into the primary equation. So our constraint is what we found right here, 2400 equals x plus 2y, and we can just simply solve for x, and that would be x equals 2400 minus 2y. Because if you subtract 2400, the sign changes, and that's why the 2y becomes negative. So, and then plug this into the primary equation. So we know that area equals x times y, as we found right here. So now we can use the x we found and plug that into the primary equation so that we isolate the variable. So area equals 2400 minus 2y times y, because that was our x. A equals 2400 minus 2y times y. And we can simplify that further by writing area equals 2400 minus 2y squared. Now, our next step, this is where things get a little bit more calculus related. Step 5. Step 5 is to find the derivative of what we just found and set it equal to 0. So the derivative of area equals 2400 minus 2y would be a prime equals 2400 minus 4y. Bring that 2 out in front. Subtract 1 from the exponent. Oops, missing a 0 there. And set it equal to 0. So 0 equals 2400 minus 4y. That's step 5. Now on to step 6, which is to solve for isolated variables. So, using this formula, we subtract the 2400. So negative 2400 equals negative 4y. We divide by negative 4 on both sides, and then we get 600 equals y. And since we know that x equals 2400 minus 2y, we now know the y, we can solve for x. So x equals 2400 minus 600, and x equals 1200. So we are almost there. We have found our x and our y. Our last step is to make a conclusion statement. So our conclusion statement is that the maximum area dimensions are 600 feet by 1200 feet. So those are the dimensions of the field with the largest area. And that is our final answer. So that last example was pretty simple, and it's just a good way to show you how optimization works. This next problem will be a little bit harder, but we'll still use the same steps and hopefully get the right answer. So, a manufacturer wants to design an open-top box having a square base and a surface area of 108 square inches. What dimensions will produce a box with the maximum volume? So again, maximum volume is what we're focusing on. So for step 1, just like before, we're just going to draw a picture. So we have a rectangular prism. Looks something like this. Rectangular prism looks something like that. And of course it's open on the top, so there's nothing right here on the top surface. And step 2 is to find our primary equation, so maximum volume. We're going to use the volume formula, and the volume of a rectangular prism is length times width times height. And since, oh yes, and we can represent that on the rectangle with x being on the base right there, and h representing the height. And we can just simply write it as it pertains to our formula as v equals x squared h, just like that. So on to step 3, we need to find the constraint. So the constraint would be the surface area of 108 inches squared. And we know that surface area, we have 4 sides plus 1 bottom, because remember, there is no top. So surface area equals 4 times xh, that's these sides right here, and the bottom, which would be x squared, so that is our surface area. So we can simplify that further, writing SA equals 4xh plus x squared. And since we know that the surface area is 108 inches squared, therefore we can write 108 equals 4xh plus x squared. So now we have our primary equation and our constraint. And on to step 4, which is to solve the constraint for a single variable and plug this into the primary equation. So step 4, we can move the x squared to the left side of the equation by subtraction. So 108 minus x squared equals 4xh, and then we can actually isolate the h by dividing by 4x, and then we come to our answer for h. H equals 108 minus x squared over 4x. Pretty simple. And then we can plug this into our primary equation. So remember that this is what h equals, and then we're plugging it into our primary equation. V equals x squared times h, so volume also equals x squared times 108 minus x squared over 4x. So we just plugged it in, and then we can simplify this by combining the x squared in the front, so that volume equals 108 x squared minus x to the 4th power over 4x. So we just took that x squared and just distributed it. And now we can divide. and simplify further, and volume equals 27x squared minus 1/4 x to the x cubed, because the x's cancel out. Oh, my bad. There's no square right here, just 27x. So now that we have done that and plugged into the primary equation, we move on to step 5. Oops, pencil broke. Step 5 is to find the derivative and set it equal to 0. So v prime equals 27 minus 3/4 x squared. And then we set this equal to 0. 0 equals 27 minus 3/4 x squared. Make sure you guys can see that. And then we can solve for our isolated variables, which that's part of step 6, but we can just go ahead and do it right here. And you can multiply by 4/3 on both sides. Oh, first you want to take the 27 and put it on the left side of the equation, so that 27 equals a positive 3/4 x squared, and you just flip the sign, and then now you want to multiply by 4/3 to isolate the x. So this is part of step 6, but we're just doing it right here. So step 6 is right here. And then these cancel out, and 4/3 times 27 is 36. So 36 equals x squared, and then nice and even, 6 equals x. Nice flat number. So with the rest of step 6 continued, solving for our isolated variables, we know that 108 minus x squared over 4x equals h. So if we plug the x we just found right here, we can solve for h over here. So h equals 108 minus 6 squared, which is 36, over 24. And if you work that out, you get that h equals 3. So we got our x, we got our h. So we have the dimensions for rectangular prism. So now we need to just do the last step and make a conclusion statement, which would be the dimensions of the box with the maximum volume is 6 inches by 6 inches by 3 inches. And then we are done. So this next problem is a little bit more tricky, but if you feel like you are confident enough to solve the problem on your own after I'm done reading the problem, you can go ahead and do that. So we are finding the maximum area in this problem. Actually, we're working with just the maximum and minimum areas. And so here it goes. A rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inches, and the margins to the left and the right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So the least amount of paper is what we are looking for. So as always, we're going to start out by drawing a picture. Of course, I'm not going to write the numbers for you because you can reference your notes and you know by now. So just put that a little bit lower. So we're actually working with two areas. We're working with the print and the stuff outside of the print. So this right here, this inner rectangle represents the print, the 24 inches, the 24 square inches of print, and this represents the margins. So these are our margins. And to the left and to the top and the bottom, the margins are 1.5 inches. So let's write that down. And to the left and the right are 1 inch. 1 inch. 1 inch. And we can represent the area in between with x and y. So we'll just call this x. So that's this area between the margins. And we can represent this with y. I know it's kind of backwards, but it's okay. X and y. So that represents the area between the margins. So first we need to find our primary equation. And it's actually interesting because we have two areas. So the primary equation is going to be the area to be minimized which is actually just A. And we know that area equals 2 plus y times 3 plus x. And we say that because 1.5 times 2 equals 3. So if we combine that with x, that's what we come up with this. And 1 plus 1 equals 2. We combine that with the y, that's how we get that. So that is our primary equation. And our constraint, of course, is the 24 square inches of print. So the constraint also has an area of a rectangle. And 24 equals x times y. You can also write it like this because this is the same thing. So our constraint is basically everything in here. And we can isolate that variable, isolate the y by dividing, and y equals 24 over x. So now that we isolated that, we can plug that back into our primary equation, and that would look like this. Area equals 2 plus 24 over x times 3 plus x. So we just plugged our y into this right here to get this. And then after that, we can FOIL, and that will help us simplify things, get things out of the parentheses. So 2 times 3 is 6, and then so on and so forth. 2 times x is 2x, and 24 over x times 3 equals 72 over x, and 24 over x times x equals just 24. So there we go. Things are a little bit simpler now. And now area, we can combine like terms. So area equals 30, combine the 6 and the 24, plus 2x plus 72 over x, so only a little bit changed there. And then we can actually rewrite the 72 over x as 72 times x to the negative 1 power, and we'll just rewrite it like that. So area equals 2x plus 72 x to the negative 1 plus 30. So now it'll be easier to find the derivative of that, and that's our next step. A prime equals 2 minus 72x squared. 72x to negative squared. And I do apologize, video did cut out there, but all we've done since video cut out is a prime equals 2 minus 72 over x squared. So we simplified it by bringing the negative x squared down to the denominator. And now we just set it equal to 0. That's the next step. So 0 equals 2 minus 72 over x squared. And then now we're going to isolate that for a single variable, which is x. So we can subtract the negative 2, and negative 2 equals minus 72 over x squared. We can then cross multiply, and then 2x squared equals 72, so we cross multiply, flip the sign on both sides, or multiply by negative 1, however you look at it, divide by 2. 72 divided by 2 is 36, so x squared equals 36. Once again, a nice even number, and the square root of 36 is 6. So also remember that x equals plus or minus 6, because that's a square root, but we're dealing with positives here, so x just equals 6. And we can solve for y, because we know that y equals 24 over x, as indicated up here. So y equals 24 over x, aka y equals 24 over 6. So y equals 4. Now, what does this mean? Well, for our conclusion statement, it means that dimensions of this page should be 9 inches by 6 inches, because when we plug back into this formula, we bring the y, which is 4, which is 2 plus 4 equals 6, and 3 plus x, which is 6, so 3 plus 6 equals 9. So we actually end up with 9 by 6. So this page should be 9 inches by 6 inches. And that is our final answer. This page should be 9 inches by 6 inches. So we have one final example. 4 feet of wire is being used to form a square and a circle. How much of the wire should be used for the square, and how much for the circle to enclose the maximum total area? So again, if you think you can solve this problem using the steps, you can go ahead and solve it and pause the video. But it will take a little bit of out of the box thinking, because there's 2 parts to it. But moving on to the solution, we have our square, and we know that a square has 2 the same sides, so x times x equals x squared. And we also have a circle, and circles have a radius, so we're going to represent our radius with r. So that's our picture. And also it's worth noting that our total area is obviously going to have to equal the area of the square plus the area of the circle. So to keep that in mind, so that'll actually directly influence our primary equation. Our primary equation is going to look like this. Area equals this area of a square. We know that the area of a square is x length times width, which can also be written x squared or s squared, depending on how you look at it, but for our sake it's x squared. And you know that the area of a circle is pi r squared. So that's our primary equation because we're looking for the total area. And now our constraint. And that is going to be perimeter because the 4 feet of wire is basically a perimeter around the square and circle, and that's what's limiting us. So our constraint is perimeter equals 4 feet. Or we can also write 4, which is what we know. We know our perimeter is 4 feet already. And it equals 4x, 4 times the number of sides over here, plus 2 pi r, because that's the circumference of a circle. So now we can go ahead and use that formula that we just found right here with the constraint and isolate our r. That'll make things easier for us. So right here, 4 minus 4x. So basically we just took this 4x over here and subtracted it. So that's on the other side of the equal sign. So 4 minus 4x equals 2 pi r. And then we can divide by 2 pi to isolate r. And r equals 4 minus 4x over 2 pi. And we can simplify that by dividing the 2. And then we just get r equals, or radius equals 2 minus 2x over pi. Voila, that's our radius. So now we need to plug that into the primary equation. So we write our primary equation, a equals x squared plus pi r squared. And then we plug in the r. So a equals x squared plus pi 2 minus 2x over pi squared. And then we can square the 2 minus 2x over pi, and that'll of course make things a little bit complicated, but we must keep moving on. Area equals x squared plus pi times, if we just simply FOIL, 4 minus 8x plus 4x squared. And that is all over pi squared. So we can distribute the pi right here into that, and then this is what we end up with. So we have our x squared as normal plus 4 over pi, because we have pi squared down here and 1 pi up here. One of them cancels out, the other one stays on the bottom. Minus 8x over pi, same sort of thing. Plus 4x squared over pi. Now, this is something that we can find the derivative of, so that's what we're going to do. A prime equals 2x, so we're bringing x squared in the front, subtracting the exponent, minus 8 over pi plus 8x over pi. And then we set that equal to 0. And then we can subtract can subtract our 8 over pi, change the sign, and it would look something like this. I think the sign got mixed up somewhere with the 2. I was copying the notes, but it looks like this. And then from there, we can bring our x out in front, isolate the x, so that 8 over pi equals x. 2 is 8 over pi. Just like that. And then we divide by 2 plus 8 over pi, and then we've isolated our x. I hope you can read that. And then we can simplify that by distributing pi to what's in the parentheses, so that x equals 8 over 2 pi plus 8. Pi is canceled out in the second term. And then we can divide by 2. In case you can't see it. So x equals 4 plus pi over 4. And you can use a calculator to solve that. And x equals approximately 0.56. So we now have our x, and that's actually a huge part of the problem. But we're not done yet. We need to plug that back into our perimeter to find the perimeter of the square. So we have the perimeter of the square equals 4x. So equals 4x, and 4 times 0.56 equals 2.24 feet. So that's our square. And we know that we have 4 feet of total wire. So 4 minus 2.24 is going to give us our circle, which is 1.76. And of course you can check that if you wish. But then we just write our conclusion statement, which we're going to just write in simple terms right here. Square is 2.24 feet. And our circle is 1.76 feet. And that is our final answer. So, in conclusion, we now know how to find optimized values of things using primary equations and constraints. Those things make our lives a lot easier. And this can be done for simple problems as well as complex problems with moving parts, like the last one when we had a square and a circle. And this can, in essence, help us with the dynamic aspect of calculus as a whole, because calculus is unlike algebra and other things because it's almost moving, and in a sense, we didn't know the optimum values, but we were able to find them out. So now we have our homework problems. The homework for this lecture is going to be page 216, numbers 7,